Hi everyone, and welcome to another episode of Organic Chemistry with Wikipedia. Today we will be talking about the reactions of alkenes. So this is very exciting because now the reactions get significantly more interesting and we get to talk about the mechanisms by which they occur. The alkane reactions were okay, like not super interesting, but as we move into more complex types of molecules, more complex and interesting things can happen. So let us get started. All right, so common reactions of alkenes. Most of the things that are going to happen when you break the double bond. So if we take our alkene, which is just this right here, what we do is we add some stuff to it, and what happens is that and these don't really have to be hydrogens, they can be whatever they want to be. What happens is that this double bond, just kidding, opens up, and we have the things that we started with, and then here we can also add something else. So usually it's going to be a hydrogen and an X component here. You can also add, well, let's just do this. We'll put two X's because you can also add two of the same thing, which we can see here in this bromination. But this X is usually indicative of like a hydrogen or a halogen, like Br or Cl, or an OH group as well. So let's talk about these different reactions that we can use to add stuff to our alkene. Okay, so the first thing that we have is what we call the addition of hydrogen halides. So the hydrogen halides are basically just your binary acids. So like HCl, HBr, HF, and HI. Are hydrogen halides here. So each of these produce a halogen. So we produce here a halo, nope, not a halogen. A halogen makes no sense. A haloalkene. Alkane. Oh my goodness, I cannot speak today. They produce a haloalkane. All right, so what ends up happening here is we take some, we'll just start with a very simple compound here. Some ethene, and add to it some hydrochloric acid. And what this does is the hydrogen just ends up on one of these CH2 groups and the chlorine ends up on the other CH2 group. So we have CH2 now single bonded. And let's do this. We'll put this in a different color because I love colors. And then we have an extra H here. And then we have a Cl here. So basically what we've done here is we just take some ethylene and some hydrogen chloride or hydrochloric acid, and we just make some chloroethane. Easy peasy, right? Same thing we can do with some larger compounds here, and then when we start with larger compounds, we end up with a little bit more variety in the things that can happen. So let's do this. So here we have propylene. And then if I add some hydrochloric acid to propylene, this becomes a bit trickier because now I have the option of putting the hydrogen on, if we number these 1, 2, and 3, I have the option to put the hydrogen on the first carbon or on the second carbon. So if I put the hydrogen on the first carbon, then what I end up with is CH3, CH2, CH2, and I end up with an H here and a Cl here. And then if I put the hydrogen on the second carbon, just kidding. So if I put the hydrogen here, then the chlorine would go here. And it matters where I put it because if I look at this compound, this is going to be 2-chloropropane. 1, 2, 3. I'll number them in the same order that we did before. 1, 2, 3. 1, 2, 3. And this is 1-chloropropane. Right? So it can go in either place. So the question now becomes, which one do we get? So what was found is that when this reaction was performed in laboratory, almost all the product was, drumroll please, Shazam, 2-chloropropane. Huzzah! Okay, so why is that? So is it just because of this particular compound? Is it all of the time? Like what is going on here? So scientists did some more research, and eventually we came up with Markovnikov's rule, which was created by Markovnikov. Shock and surprise. So what Markovnikov's rule says is that whenever you're adding something to an hydrogen halide to an alkene, and this doesn't just have to be a hydrogen halide, it can also be water or a halide. It can be other things too. I can't think of any. H2S is another one. So it doesn't matter if you are hold on. HOH. Let me rephrase that so that we can see what it looks like, because this would be H and an OH group. So here, when we have these things that we're adding, what scientists have found is that the hydrogen will always bond to the carbon with the greatest number of hydrogens. So the hydrogen is sort of attracted to its peeps, and so it's like, oh, these are where all of my hydrogen people are, I'm going to go over here with the hydrogen. And then all the substituents bond to the more substituted carbons. So the substituents are like, I don't really like to hang out with hydrogen, I like to hang out with things that aren't hydrogen. So it bonds to the carbon that doesn't have as many hydrogens. It's got more substituted stuff. And that substituted stuff may just be other carbons. It doesn't have to be like another halogen or a hydroxide or a double bond. It doesn't have to be any of those types of things. It can just literally be more carbons. But if there is a carbon that if the number of hydrogens are not equal on both carbons, then whichever carbon has the more hydrogens will get the hydrogen and the other carbon will get the other substituent. If there are an even number of hydrogens on both, like if both of them have like one carbon and one hydrogen, or one of OH group and one hydrogen, like if they're the same, there's no preference, then there's an equal mixture of both products. So then we end up making about 50-50 of each instead of predominantly one over the other. So what we're going to find is that Markovnikov's rule applies to a bunch of different things, not just this halogens, not just the hydrogen halides that we look at, but also when we talk about alcohols, this will apply to that as well. All right, so that is how we know what it is that we're going to make. So now we're going to talk about mechanisms. So we just described what happens in that reaction, but what we failed to mention is how it happens. So if we're trying to figure out how these things occur, then what we're looking at is the mechanism. All right, so for the mechanisms, when we draw these, we use a curved arrow to show the movement of electrons. So in order for a reaction to occur, these electrons are kind of what is guiding what's going on. So we kind of trace the path of the electrons to figure out what is going on in our reaction. Oftentimes, those flow of electrons will produce what is called a carbocation. And I know that this looks like carbocation. Fun fact, when I was in college, I often thought it was carbocation whenever I would read it, because sometimes I did not listen in class. Oh no, and I missed, I guess, the part where he explained it was a carbocation. All right, so carbocation is not stable, but it is an intermediate. What does it look like? A carbocation looks like this. It's got it's got 1, 2, 3 things attached to it. And then because it is missing that fourth thing, it's got a little positive charge here, because it's missing missing the fourth thing here. So this is no bueno. This is not stable, which is why it's produced in a mechanism. So these are intermediates in a mechanism because they don't last for very long, like they're created and then immediately destroyed again. These carbocations can be primary, secondary, or tertiary, depending upon what is attached to it. A primary would only have one carbon group attached, or we'll call it an R group. We'll only have one R group. A secondary will have 2 R groups and a hydrogen. And then the tertiary will have all 3 carbons are attached to a, this doesn't need to be prime, there we go, will be attached to here. And I forgot the most important part of my carbocations, which is that they are positive. So we have a positive here, and a positive here, and a positive here. So what we'll find is that in some of these mechanisms that we look at, we are going to be producing some carbocation action up in here. Okay, so now that we kind of have that done, let's look at the mechanism of how hydrohalogenation occurs. Yay! I can see that we are all super, super excited. Okay, so let's do this. Let us begin talking. So let's start with what we have, which is ethylene. And we're just going to do the simplest version of this because nothing else other than what's attached to the double bond matters. Like you could very well just have like another R group that's happening over. This could just be like CH and then like an R group over here. It makes no difference what we've got going on because it is only going to impact our or double bond. Okay, so here we have hydrochloric acid, so or hydrogen halide. We've got this chlorine happening here, and we've got this positive hydrogen here. So the double bond electrons are like, ooh, look at this hydrogen. It's a bit positive over here. It is going to attract onto that. And I'm missing, I was forgetting something. There we go. So our positive hydrogen, our double bond here grabs on to that. And what ends up happening here is that this hydrogen attaches itself to one of these guys. So if this was something different, something larger, then this is where Markovnikov's rule would come into play. This hydrogen would attach itself to whichever carbon had more hydrogens on it. But since these are exactly the same, it makes no difference. So here we're going to attach our little hydrogen onto here. And so we have CH2, CH2, and then we have this hydrogen coming off of here. All right. And so now that we have this hydrogen coming off of here, this is now completely stable. It has 1, 2, 3, 4 bonds, but this only has 1, 2, 3 bonds. And so this is our carbocation. So if we kind of draw this out, we can see that this would be hydrogen, 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 hydrogen. And we can see here that this is where our positive would lie. All right, so we end up with this lovely little carbocation action here. And so then we take our carbocation. And so the CH3 is good. So we're just going to draw this right here. So we have this, and it's got a positive charge. And then this is going to react with my chlorine from before that I did not use in the previous part. I use a different color here. So I did not use that chlorine in this first step here, but I'm going to use it in the second step. So here I'm going to now take these electrons from this chlorine are going to be attracted to that carbocation, and it is going to attach itself to that empty spot here. So now I have this, and voila. And so I have now produced this lovely, chloroethane molecule. All right, so this is our basic mechanism. So if we look at something that's a bit more complicated, let's look at an example. Let's look at 1-butene. So we have CH2, CH, CH2, CH3. 1, 2, 3, 4. Yep, so this is 1-butene. Right. So if we have 1-butene, and let's react this with some hydrogen bromide. We'll mix it up a bit. All right, so then we've got some H plus and some Br ... minus. All right, so here now, our double bond is going to attract our hydrogen. All right, so now we have to pay attention to Markovnikov's rule. So with Markovnikov, I can either have the hydrogen go on the outside here. So I have two options. So I can go CH2, CH, CH2, CH3, and I put the hydrogen here and have the carbocation here. Or I can do CH2, CH, CH2, CH3, and I can put the hydrogen here and have the carbocation here. All right, so Markovnikov's rule says that we're going to do the first one, right? So this is the favored one. And then here we can kind of see why, because if I'm going to have a positively charged carbon here, like this is not very stable, but the more carbons I have surrounding it, the more things that are attached to it, the greater the stability becomes. So it actually becomes a more stable carbocation here because I've got these surrounding carbons around it. Whereas here, this carbocation only has one carbon surrounding it and mostly just hydrogens. So it is less likely to be super stable. All right. So that is why Markovnikov's rule works the way that it does. So this is our favored. So this is the only one that we are going to make. And so then if I go down to my second step here, so I'm going to continue on. I do CH3, nope, yep, yes, CH3, C, H, and then here I have CH2, CH3. So I've just drawn this a little bit differently so we can kind of see where our carbocation falls here. And then I'm going to add to it that bromine from before. And so my bromine is able to attract, gosh, this is super, there we go, is able to attract itself to this positive, and I end up making CH3, C, H, Br, CH2, CH3. And this is drawn very, very wonkily. This is basically just this. CH3, C, H, Br. Actually, we can just do this. CH, CH2, CH3. And so what we've made here is 2-bromobutane. Excellente. So the carbocation situation here is, again, like another way to look at this is that the higher the designation of the carbocation, the more stable it is. So tertiary carbocations are more stable than, or greater than, that's less than, or greater, or more stable than secondary, or more stable than primary in terms of stability. I don't think I spelled that right, but we get it, right? Yes. Excellent. Hooray. Okie dokie. So, if we were dealing with something where there was no preference, so like let's say that we had 2-butene. Just kidding. So if we look at something like this, we can look at this, and if we were to react this with, let's do hydrogen fluoride here. So here, if I take this hydrogen, it doesn't matter what I've got because I've got one hydrogen attached to here and one carbon, one hydrogen attached to here and one carbon. So there's no preference for what I'm going to make. So I'm going to make 2 equal mixtures of, or actually, hold on. So I make, it makes no difference where I put it because I make the same compound. This is not a good example. So in this particular case, I would make the same compound because I would get CH. This is wrong here. This is CH3. And then like that. So if I had this, then I would make CH. And then this would be fluorine here with this. And then if I made the other one, if I put it on the other carbon, it's exactly the same compound I just counted from a different direction. So here, this is 1,2-fluorobutane. This is still 1,2-fluorobutane, so it makes no difference. But if we were to look at, if I changed it up and did this, CH2, CH3. If I did this, then again, it wouldn't make any difference which carbon I put, or where the hydrogen goes, because it's still one hydrogen here and one hydrogen here. So in this particular case, I would make an equal mixture of both compounds. So I would have CH3, CH2, CH, CH3, CH3, and then I would put the fluorine over here. Or I could have CH3, CH, CH2, CH2, CH3, and the fluorine would go over here, and the hydrogen went on the second one. So here I would make 3-fluoropentane, and here I would make 2-fluoropentane. And both of these would be in equal amounts because the hydrogens attached are the same. Okay, excellent. So that is our hydrohalogenation. Let's move on to the next reaction here, which is just plain halogenation, no hydro involved here. So this reaction only occurs at room temperature in the presence of a solvent, and it will only occur with bromine and chloride. Iodine is too big and fluorine is too electronegative in order for this reaction to occur. So we have only with bromine and chlorine, and these solvents do not matter. Like, you can use the CH2Cl2 solvent with bromine as well as with chlorine. Like, it makes zero difference. So here, when we do this reaction, we get CH2, so we'll take some ethane, and we'll add to it some bromine in the presence of some CCl4. So whenever we have a catalyst, we write it up above our arrow. And then here, because we are just adding plain bromine, we actually just brominate both of them, and so we get a double bromination occurring. So here we get 1,2-dibromoethane. So we just add a bromine on both of those. So basically this double bond just opens up, and then we end up with bromines on either side. Okay, so let's look at the mechanism of this. There's not really much more to this in terms of, like, there's no Markovnikov's rule here because you're just adding it one on one side and one on the other side. There's no preference because each one gets one. Everybody's happy. Hooray. Okay, so let's take a look at the mechanism for halogenation. All right, so we'll start off here with this, and then we will draw the Lewis structure of our bromine here, where we've got all of these luscious lone pair surrounding my bromine. Okay, so what happens? So this double bond is going to extend out and attach itself here. But because of the way that these bromine already have all of their electrons, it is a bit precarious in terms of what happens. So what ends up happening is that we actually then take those electrons and put them there. So this double bond extends out to here, and then these electrons end here. But because of this electronegativity of this or because of all those electrons of that bromine, we don't end up getting a carbocation. We end up with this lovely thing that is called the bromonium ion. So we end up with a triangular situation. This is new and different. And then that ends up being a positive charge on that bromine here. So this is a bromonium. I know that, like, it goes against everything that we have ever learned before about where, that's not B, it's supposed to be Br, about how halogens do not form positive charges, but as it turns out, in certain circumstances they can. So, but it's not stable. So here we have this lovely cyclic creature here that's got a positive charge on it. And then we ended up with that bromine grabbing those 2 electrons from that that single bond that was attaching them, and so we end up with a negative bromine. And so now, since we have this occurring, draw that. This is not. There we go. All right, so now that we have this situation and we have the bromine here, I'm sure you can guess what happens here. This negative attracts itself to not actually the positive. It really attracts itself to this CH2 here. And then what ends up happening is that this bond here ends up over here to stabilize that carbocation. And I put too many lone pair on here. I'm just now realizing I got too much stuff going on. Yeah, that makes more sense. Because we had 3, and yeah, that's fine. Okay, so we have this situation that is happening here. This should actually be it only had 6? Yeah, okay. All right, and then we end up with this situation here where we have a bromine on one and a bromine on the other. And so that is how that occurs. All right, excellent. Okay. And then the last reaction that we are going to be looking at is what we call the acid-catalyzed hydration reaction. So this reaction here is a where we take water, because it's hydration, and we use an acid catalyst to create an alcohol. All right, so this is going to be, if we just take the simplest form of this, we have CH2, and then we add water. And then generally the acid that we use to catalyze this is going to be H2SO4. If I use a hydrohalide like hydrochloric acid or hydrobromic acid, then what I run into is the water won't do anything, and I'll just produce the hydrogen halide. So I can't actually use any kind of like HCl, HF, HBr. I can't use any of those acids. I have to use something that's not going to produce hydrogen halide. So sulfuric acid is one of the more stronger acids that is not from a halogen, so we use that one, and it also doesn't react with anything else. Nitric acid is also strong, but we don't use it for reasons that we will learn down the line. All right, so then basically what happens here is that water is just HOH, right? So one of the H's comes here, and the OH goes there. So we end up with H2OH. So this is just CH3, CH2OH. This is ethanol. We don't know that yet because we haven't learned about alcohols. Markovnikov's rule applies here just the same as it did before. So like if we are looking at propene, and we do this. That was very wonky looking. If we do this, so then our water, our hydrogen here, will attach itself only here, and the hydroxide group will attach only here. So I will always make this compound. I will never make this compound. CH3, CH2, CH2OH. All right, so I never make the one version of this, like this is called 1-propanol. I always make 2-propanol, so it's always on the second one because of the hydrogen affiliation here. So all, yay, none, no. Okay. So let's talk about the acid-catalyzed hydration mechanism. All right, so This is a more complicated situation. We have multiple steps happening here. So let's look at it a step at a time. So step 1, we're going to take some of this, and we'll do it with, let's look at the propene, so we can Markov this. Okay, and so what's going to happen is I'm going to take this and I'm going to react it with an H+. This is from the acid. So this is from the H2SO4. All right, so this acid here, so I'm going to take this reaction and I'm going to then, my double bond is going to reach out to that positive hydrogen to produce a carbocation. So my more stable carbocation is going to be on the inside carbon, not the outside. Hydrogen goes where there are more hydrogens. So I have CH3, CH, CH2 now, and there is a carbocation there. And hydrogen here. All right, so here we have this is a secondary carbocation because I've got 1, 2 things attached. All right, so now my carbocation, my carbocation from here, and I'm just going to start drawing this like that. So I have this carbocation here. Now it can react with the water. Do a different color. So water looks like this with our lone pairs here. So my lone paired water attracts to that carbocation situation here. And then it just attaches itself. So we end up with CH3, CH, and then literally the water just attaches itself and it creates this positive situation here. Okay, so got that positive action happening here. Oh, and let's finish this out. This is CH3. Okay, this is, fun fact, called oxonium. The oxonium ion. All right, so now we have this crazy looking thing. So we've got to get rid of one of those hydrogens. So we're gonna come down here with our wonky looking creature here. Oopsies, this goes here. Zoom, and it's positive. And we are going to take our, all right, so let's go back up here. So this was H2SO4, right? So this H came from here. So we ended up with HSO4 minus left over from this reaction because we took one of those H pluses. So this HSO4 minus now can come in, and because it's a negative, it can come in here and it's going to grab this hydrogen, and let me use a different color here. So it's going to grab that hydrogen, and then this will just become lone pair on the oxygen. So we end up with CH3, CH, CH3, OH, which now has a complete octet, and the original H2SO4 that I started with. All right, so just to kind of go through that one more time, I'm going to pluck a hydrogen off of the H2SO4 to create the carbocation here, and then some of this, the HSO4 minus is left over here. Then the water will come along. The lone pair from the oxygen on the water will attach itself to the carbon to remove the carbocation, making the water positive. And then the leftover acid will then grab the hydrogen again, which allows those electrons to go back to the oxygen to create the alcohol. And then I end up with my original acid that I started with, which is why it's a catalyst. None of the acid actually gets consumed by the reaction. So even though it's used in the reaction, it's a catalyst because I end up with the same amount that I started with. It's not the same hydrogen though, because the hydrogen from the acid is actually now attached. So this is the hydrogen from the acid. One of these is the hydrogen from the acid is here. And then the hydrogen that ends up in the new acid is actually from the water. So the second hydrogen here started with the water. So it's not the same hydrogen, it's a different one. Fun fact, the tracking of the hydrogen can come from what we call deuterated water. So the deuterated water just has the water is a deuterium, so it's heavier, it has an extra neutron. And so because the water hydrogen has an extra neutron, we can kind of see where it goes, and we end up making this sulfuric acid ends up being a deuterated sulfuric acid because one of the hydrogens in here is more massive than what it started with. So fun fact, like that's how scientists know that this happened. You can make heavy water, literally heavy water, because it's made with hydrogens that have extra neutrons. So there you go. That's how we know that this mechanism is valid. All right. And then the very last reaction is the addition of hydrogen, which is called catalytic reduction or catalytic hydrogenation. This one is very easy. You take some alkene, and to it you add some hydrogen gas, and then you just saturate it. So you are losing the double bonds, and you will lose all the double bonds when you do this, if you have dienes or trienes as well. So these double bonds just disappear, and you just end up with the alkane. CH3, CH3. You just make some ethane. Ethane, not methane, sorry. And that's it. This needs to happen in the presence of a metal catalyst at high pressure. Usually the metal that we use is something like platinum or palladium, because they're inert metals. We don't want a metal that is going to react with anything or oxidize or any of those things. And so we like to choose things that are not going to do that. And experimentation has shown that platinum is actually really great for this. So the mechanism for catalytic hydrogenation, as it turns out, is not really something that you can draw with arrows and understand. There is something about the way that the metal, the surface that it provides, that makes this reaction happen. So basically, like the alkene will attach itself to the metal, which it can do that because if you remember, those metals have all of those free-floating electrons that are present, and so they kind of attach itself to here, and then the hydrogens attach itself, and then the hydrogens then attach themselves to the alkene, and it breaks apart that bond. And that's all that we can really say about it. There's not really any kind of mechanism or tracking or anything like that that we can do. This is what it is. So, as promised, these are our reactions of alkenes. I forgot here. I said it, but I forgot to put it. Platinum, and then it's usually at high pressures, which is 3 atm is high enough for this. I forgot to mention that. Okay, so that is all of that, all the reactions of alkenes that we're going to talk about. This has been another episode of Chemistry with Wikipedia, Organic Edition. I hope you learned something, and until next time, keep on chemin'.